This lecture is part of an online course of multivariable calculus, and we're going to talk about higher partial derivatives. So if we have a function of three variables x, y, z, then the partial derivative of f with respect to x, we define this as f of x plus delta x, y, and z minus f of x, y, and then z over delta x as delta x goes to 0. Basically, we just have change in x, and y and z are fixed, as you see, and we are going to consider the change of f, the rate of change of f, as x is just changing and y and z are holding fixed. So similarly, we have like this definition for partial derivative with respect to y or partial derivative with respect to z. Let me write with respect to z. F of x, y, and z plus delta z minus f of x, y, and z over delta z as delta z. Actually, this is also delta z as delta z goes to 0. You see, and here x and y are held fixed and z is just changing. Okay, so to compute this, we're just gonna regard y and x constant, and we differentiate with respect to z. With respect to z. That's how, if we have a function, for example, x, y, and z, like x, y, z cubed plus y squared, if I want to take derivative of that with respect to z, that we show it also by f sub z, the same thing with respect to z. I'm gonna assume that x and y are fixed, just some constant, and z is just the variable. So it would be the constant times 3z squared, so it would be 3xy and then z squared, and since y is constant, y squared would be 0. Okay, now let's talk about the second partial derivatives. And so let me have a diagram for you. If we have a function f that is a function of two variables x and y, we can differentiate this with respect to x, and we can differentiate it with respect to y. The function f sub x and f sub y, both of them, these both are functions of x and y. So we can treat these two as a function of x and y, and now we can take derivative of them again. So I take derivative of that with respect to x, and I'm gonna show this by this notation, the second partial derivative of f with respect to x, or I can differentiate this with respect to y. The same is true here. I can differentiate this function. This is the function of x and y. I can differentiate this with respect to y, or I can differentiate this with respect to x. Okay, now what are the definitions for each one of them? So partial derivative of the second partial derivative of f with respect to x squared, it's like I have partial derivative of f with respect to x, and then I took derivative of that with respect to x one more time. So I just here assume that this is a function of x and y. As before, I just take derivative of that with respect to y. I can write this like that. I have f sub x in here, and I take derivative of that with x. I get f(x)(x). Similarly, I can find the partial derivative of the second partial derivative of f with respect to y and x. What is this one? This one is like I have the partial derivative of f with respect to x, and then I took derivative of this function with respect to y. In the subnotation, I can write this one as fx, and then I took derivative of that with respect to y, so I write this one as fxy. Let me write the other two as well. So the second partial derivative of f with respect to y squared, it would be partial of f with respect to y, fy sub y, and if I want to write partial derivative of f with respect to x and then y, it would be like I have partial derivative of f with respect to y. It's a function. I take derivative of that with respect to x. In the subnotation, I have fy, and then I took derivative of that with respect to x. I write this with fyx. Okay, let's look at one example. The function fxy is equal to x cubed y plus y squared. Now, the partial derivative of that with respect to x, I just treat y as a constant. So I get 3x squared. Y is just a constant. And then derivative of the constant is 0. F sub y would be what? I take y as the variable, x is a constant. So I get x cubed, and then y is a constant. Y is the variable, so I get plus 2y. And now if I want to write fxx, I treat this just as a function, and then I take derivative of that with respect to x. So I get 6x, y is a constant. So if I have fxy, it would be like what? I assume that this is just a function. I take derivative of that with respect to y, meaning that x is a constant, so I just have a constant times y. It would be just a constant, 3x squared. How about fyy? Just the second partial derivative of this function with respect to y. I just assume that this is a constant, 0. Derivative of that with respect to y, just 2. Fyx, I just take derivative of that with respect to x, so I get 3 x squared. You may notice that this one and that one, they're the same. Is it a coincidence, or this is a general case? I'm gonna write that fortunately fxy is equal to fyx, assuming that they exist and are continuous. In our previous example, both of these functions, they are polynomial, so they exist and they are continuous. That's why these two are equal to each other. And this is actually a theorem. This is Clairaut's theorem. And Clairaut's theorem says that if fxy and fyx are defined and continuous in the neighborhood of xy, then fxy at the point x and y is equal to fyx at the point x and y. And in the function of 3 variables, we have the same idea. So as a note, if we have in a function of three variables, we have fxy is equal to fyx, we have fxz equals to fzx, and we have fyz equals to fzy, assuming that all of them they exist and they are continuous. Okay, and as the second note, I would like to mention if we have the higher partial derivatives. So higher partial derivatives. For example, if we have f of y, x, and then z, so what it means, this is the fourth derivative. As you see, we have the function fy, we have the function f, we took derivative of that with respect to y, then we took derivative of that with respect to x, then we treat this as a function, we take derivative of that with respect to x again, we treat this as a function, we take derivative of that with respect to z. We just keep differentiating with respect to the given variables. On the next video, we're going to solve some examples on how to take partial derivatives.